start talking about first. So one thing that's useful for next assignment is this command mesh grid in Python. So what I wanted to do was give you guys an example of mesh grid. So let's make a vector in range. So I'm going to make a vector -5 to 5 with a spacing of 0.1. And this is just an x vector that goes from -5 to 5 with some spacing. And then I'm going to make a y1. And then I'm going to use this command mesh grid of xlin, ylin, right? So let's run it. And then, so if we look at xlin, it's kind of what you expect. It's just a vector that goes from -5 to 5. But if I look at xm.shape, what does mesh grid return? It returns a 2D array, actually. So yeah, so it's 100 by 100 here. And I can plot, so plt.imshow. So let's just see what it looks like. So it gives me the x values, so from the lowest to the highest. So that's why it looks like a horizontal gradient. And if I look at the y1, then, whoops, why did it do that? Let's run it. Then now I get the y values. So what this mesh grid did is it made 2D arrays where everywhere in the array the xm is the x value and the ym is the y value. But I have a 2D array, so I can do calculations with it very easily, where I'm just multiplying or adding or calling functions on these 2D arrays. So an example might be, so let's take the sign of something. So xm squared plus maybe half ym squared. Yeah, sure. Why not? So this is the sign, kind of the sign of some weighted radius. So I'll run it. But now I can plot .imshow of z. And z is now a 2D array, but I did the calculation all over the place. So it's like you instantly can do a calculation on x and y everywhere with one line. This is really good. So so imshow is one way to do this, and I can plot let's see, color bar, and we can get the, find out what the z values actually were here. And there's also this handy command. So contour F. Sometimes, so some of these images show, so one of the problems with displaying an image is often, so if you look here, you see the top left is 0. And so it increases vertically down. So these are indices, and the convention is you show an image with the indice on the top left. And so there's always this ambiguity on whether you plot y increasing this way or not. So if y is a coordinate, it would increase. So, but I gave x and y as vectors, so I can plot the array with xlin, ylin, and z, and it should now plot the x values and the y values and the contours all consistently. And if we want a color bar, we can add the color bar also. Redo that. Okay. So why is this relevant for your current problem set? So let's go look at the current problem set. So and I don't know if you guys have looked at this yet, but so we have the numerical implementation for this reaction diffusion equation. And so let's look at the object that I wrote for this. So the reaction diffusion equation for both the Brust-Litter model and this other one, the Gray-Scott model, they depend on parameters. And so here we have the parameter alpha and beta and the diffusion coefficients. So they're stored as internal data in the object when you initialize it. And then there's this RD type, which I gave reaction types so that it knows which reaction equations to call. And I think I wrote the Brusselator one, and I asked you to write the Gray-Scott one. It's almost the same. And then you keep track of the horizontal grid spacing and the time step. And I think I wrote it so you could advance multiple steps, integrated steps between each output display. And then there's some kind of initialization routine. So I initialize. And then this is stuff if you want to animate it with this animate command example for animating in HTML. You don't necessarily have to use that. And so I force the axes being equal so that it looks nicer. And then there's, shows. So I'm using image show again, but with different color maps so that if you wanted to, you could tell U versus V. And then here's actually a little bit of a check for checking a CFL condition. So if you, it's rough, it's not exact, but it may give you a warning that there's a violation of the CFL-like condition for diffusion here. So then we initialize the UV. And what I find with these reaction diffusion equations is they're kind of persnickety about their initial conditions. So this is something that somehow is missing from a lot of the literature. So it's just, I found, making sure that I got nice patterns, that some of them, like the Gray-Scott model seems to like initial conditions where U is near 1 and V is near 0. It just gives you nicer behavior. And then I randomly set some points not to be that. And the Brusselator model was a little bit more robust. You could start with random initial conditions and then it would make nice patterns. So I wrote you some initial condition generators that I knew worked so that you didn't have to fight with that. And here's the update, which just takes time steps. And then an update n steps takes n time steps, because often you're taking a lot of little steps before you see anything interesting happen. But you always have to check everything. Whenever you're writing code, you have to check that a single time step did something sensible. And so these are written separately. And this is the initialization for the animation, and this is the call routine for the animation. And this just returns the U and the V arrays back if you want to display them without using the animation, like just plot them on the screen. So if you get bored, the animation is kind of annoying. If you don't like it, just plot images. So these will return the images, so you can do that directly. So that's the object. It's kind of this big thing, but let's go up and look at the reaction equations. So this is the Brusselator model. So this is this alpha minus beta times U. So U and V are arrays. Alpha and beta currently are numbers, assuming you could pass numbers, but you could actually pass arrays as alpha and beta. And that would give you slowly changing parameters for the model as a function of position in the array. And so that's why I'm saying, hey, mesh grid, useful. So this is why it's useful, because you can make alpha and beta be changing. So that at the bottom here, I added some examples. And so this is a sinusoidally varying alpha horizontally and a vertically varying, sinusoidally varying vertical beta matrix. And then so all you do is then you pass a matrix with these slowly varying things, and alpha only varies this way, beta only varies that way, and then you can make something fairly quickly that looks like that. This is how I made that, right? I used the mesh grid command. But I was looking through my solution, I realized many of you haven't seen mesh grid yet, and so that's the reason it's handy. Okay, so what's the next topic I want to talk about? Yeah, so before we go back to the whiteboard, I wanted to show you how many people have accounts on GitHub. 1. Anybody else?
I do, but I forgot the login.
Oh, okay, yeah. So, hey, Kwon, why do you have an account on GitHub?
Because we can share code and help each other.
Yeah, so it's really good. So this is my account on GitHub, which, is a little bit out of date, but I have various repositories on here. And so often I use it as a repository for papers. Like if I write code for a research paper and somebody might want to see it someday, I use it to archive how I generated the results in the paper. And that way somebody later on might, maybe I might find a mistake in my paper. It could be caused by some coding error. Or somebody might want to reproduce your results and then realize they can't. They need to check your code and find out why. So repositories for code are useful. Sharing code. So if I go into one of these repositories, I can, on this green thing, I can just ask, I want to download it all. And then you can look at, you can look at the code by clicking in here and you'll see the code come up. But you can also just instantly download the whole thing. So it's really helpful to share code. So instead of making a tarball or whatever it is, archive thing, and posting it somewhere for people to get, it's much faster. Just upload it to GitHub and say, here's the link, go get it off of GitHub. So that's another reason for it. And it also has these nice ways where you can collaborate with code. So it's actually designed for collaboration, where if you have a really big code, you can have little pieces where everybody's working on different pieces and you're trying to make sure you branch the versions and keep track of version control and stuff so that one person doesn't wreck the code for somebody else. So other nice thing, like here, this is a JavaScript, and GitHub will host animations. And so this is a code that instantly connects to an animation. So it will launch the code. And this also is from a paper I wrote, this actually published this year, on self-propelled particles and how they interact with the boundary. And it gives interesting phenomena after a while if you wait long enough. But the code itself is here, so you can just click on any of it and read it if you want to see. So other reasons for being in GitHub. So all of the people in this class are probably interested in computational techniques. So that's a useful tool for lots of things. So many of you are going to be looking for summer jobs. One thing employers look for is they were like, does this guy know how to code? Or girl, does this girl know how to code? They go click on your GitHub account, take a look at what you do. So it's really good advertisement professionally. So another reason, make a GitHub account, post whatever you've got on it to make sure you have an internet presence professionally. So I would say anybody who doesn't have a GitHub account, make one. There are a lot of reasons to do it. It doesn't have to be GitHub. It could be some other site, that's GitHub is now owned by something nefarious, probably. It used to be more grassroots, but it's still used by the community. So, all right. So the other thing here is licensing. Okay. So now I'm urging you to make it possible to share code. So I have most of the licensing I'm using are the MIT license. So I went to look at, is there helpful, why? Does anybody know why you worry about licensing? Anybody have an answer? Okay, what if you don't license? Does anybody know, like, just post code on GitHub? You don't have to have a license up, but what if you don't? What is it?
Like, advice from my community is that if you don't license, if you find a repository that doesn't have a license, do not use their code. Yeah,
okay, so there's a legal reason for that. And the reason is that anything that's not obviously licensed, the owner, it's copyright owned by you, by whoever posted it. And you may not have permission to use it. So people could possibly, if you use somebody's code that has no license, the assumption is it's copyright protected and you could be sued for using it. Okay, so no license means you're not sharing your code all that well because you're not making it available for people to use. So, so if GitHub links to this, which is not a free site, so it's a com rather than an org, so I was kind of confused, but the information didn't seem to be all that bad. So I looked up in GitHub, why should you include a license? And they make it easy for you to choose some standard ones. So, I want it simple and permissive. That's the MIT license. So it gives you copyright. You have copy, you own it, but anybody can copy it or use it. And including they can put it in closed source versions. So, so there's this issue about free software. So free software is trying to encourage people to share their software, and so they want to make it possible for people to share software. But sometimes people don't want their software being taken, put in something else that then is sold and is private. And so there is a license for that, and those are like the GNU GNU public licenses let people do anything they want with it except distributing closed source versions. So if you're like very political about free software, then you would choose that one. If you click on one of these things, it gives you all these information. Commercial use is allowed, distribution, modification, private use. And there's certain limitations, like the MIT license says things like there's no warranty. If this screws up, it's not our problem. So I'm not sure how legally binding anything of this is, but there's this caveat there. But it's trivial if you're posting on GitHub. There's a drop-down menu, you type in add file license, and it will give you these choices of standard ones, and if you wanted to modify them, you can. So just saying you should know about this stuff. So if I'm encouraging you to get a GitHub account, I'm also encouraging you to make sure that all your code has some kind of standard license on it, and then you should read up on the history or the current situation for using, a little bit. You don't need a lot. So one of the reasons for the MIT license is to make it easy to have a license that's considered, will allow your code to be shared. Because sharing code is useful for lots of things, like collaborating or just helping other people set up stuff. And in this case, will help all of you guys get good jobs because you'll be able to show that you have certain expertise in software. Okay, so I think that's the main thing. What else was anybody have any questions? Hey, Kong may actually be more up to date on things than me. No questions? Okay, so let me stop sharing. And now I need to go to this, and we need to shift over to the whiteboard. Try and make myself type slowly, which is the whole purpose of the whiteboard. So there's two topics that I wanted to talk about today. The first one was so I realized last time when I was ending lecture that I hadn't really explained that last bit where I was talking about the temporal behavior of the Brustolator model. So let me just remind you what we talked about last time. So the topic of this week's problems, or next week's problem set, this week's problem set, is the reaction diffusion equations, which are models for pattern formation. And so what they look like is a diffusion equation plus some reaction equations. And so let me remind you, the Brustolator model, or all of these models involved two. Try and actually involve two concentrations of two things. And then we had a diffusion coefficient with a gradient, some other diffusion coefficient gradient, plus reaction terms like this. So these were what the reaction diffusion equations look like. So so then we talked about so how do you explain why they give you spatial patterns? And then there was this other issue about temporal instability. So so what we did is we went and found the steady state solution, which you can also think of as being a fixed point for the model. And so that was something that gives du dt and dv dt equals 0. And then we looked at solutions near that, we looked at perturbative solutions that have time-dependent and spatial variations. We used, we wrote the spatial terms in terms of a wave vector, so e to the ikx. So the idea is you start off with some small perturbation that's sinusoidal, and then you look and see if it grows or not. And that involved expanding near the fixed point and looking to see if depending upon the spatial wavelength, if the if the time dependent part grows or not. Okay, so because we were looking at small perturbations, we linearized the equation, which means we expanded solutions. We took U is U0 plus U1. We assumed this was the steady state solution or the fixed point, and this was small, and we did the same thing for V. So we put those in the equation and then expanded to first order, and we got another equation, which we then if we assume that U and V went like this, e to the I, no I, t plus I kx plus I k y. We looked for things that had positive gamma that gave us exponentially growing solutions after we linearized. So the next thing we did is then we looked, so the next part when we looked at the temporal behavior, we ignored the diffusive part, so let's get rid of this. And we looked at this equation, just these. And then again, we looked at the behavior near the fixed point. So in this case, you can look at think about U versus V. And if du dt is 0 and dv dt is 0, then, so this is u0, comma v0. It's a point on this plot where there's no change. And so that's why I call it a fixed point. And then what we did is we expanded these solutions near the fixed point. So then this is f of u0, v is fu of u0 plus d fu du times u1, where u is equal to u0 plus u1 plus df u dv times v1, and the same thing here. So because it's a fixed point, these two guys go away. And this is V, V1 plus df V dv V1. And now we can rewrite this whole equation to look like this. dw dt is equal to J times W, where W is this, U1, V1. And J looks like this. It's a matrix. df v du df v dv. And this is all evaluated at u0 v0. So this thing is the Jacobian matrix. Okay. All right, so the part that I thought was unclear was jumping from this and it's immediately talking about eigenvalues. Especially since some of you may not have had much linear algebra yet. So let's look at this equation. So where W is a vector and J is a 2x2 matrix in this case. So if there's a vector V such, so I'm going to make this an eigenvector with let's call it d lambda, with eigenvalue lambda. So if it's what's the definition of an eigenvector means that this is true. So this is a matrix times the vector is equal to a number times the vector. So let's put that into this equation. So this J omega is lambda v lambda, so I can go dv lambda dt is equal to lambda v lambda, and a solution v lambda of t is equal to v lambda, which is the vector at time t equals 0, e to the lambda t. So if I have an eigenvector of the Jacobian matrix, I automatically get a time-dependent solution to this equation. And if lambda, so lambda could have a real part or a complex part, but if it has a positive real part, then it's exponentially growing. And so we're looking at solutions near the fixed point. So there's in general 2 eigenvectors. Sometimes there's not always 2 eigenvectors, but in general, often 2 eigenvectors, 2 different eigenvalues. And so when I started drawing these plots, what's the trajectories look like? So we have a fixed point, and if I look at U versus V, so there's no motion there. If both eigenvalues are complex, they have to be equal and opposite, so the solutions are sines and cosines. Then you get little oval solutions, so it looks like a harmonic oscillator. But if one of the eigenvalues both have real parts, and there's no complex part, then there are 2 directions, each one set by that. So these are vectors in this space. So that means the eigenvectors are actually directions on the UV plane. And so if they're both positive and there's no complex part, then the trajectories, they often curve actually, depending, and they curve because one of the eigenvalues can be bigger than the other one. So that is like an unstable node. This is he calls an unstable node. And that means that trajectories leave the vicinity of the fixed point. So it's unstable. If the eigenvalues are negative, it's like you have a minus sign here, then things attract to the fixed point. And so you just reverse all the vectors and you have things going towards the fixed point. And if the eigenvalues have some complex part and they are positive, that's when you get, so this one is a stable node. So then you get, so if we have positive and complex, then you get this type of thing, which are the unstable spirals. And those are the ones that the Bruselator model has for a particular parameters range. And the condition is you have to find the eigenvalues and then you can figure out when that happens. So that's what I did last time, but without explaining why this gives you that. So I wanted to kind of say that a little bit more clearly this time. Any questions about the temporal instability of the Bruselator model? I find the temporal part really interesting. Like when it starts flashing, I was like really curious why. So, okay, so does anybody have a question? I did not hear anything. Speak up if you have a question. Okay, so I'm going to move on to the numerical implementation, which is in here somewhere. Where's my, never mind. Numerical implementation, page 11. It's like these notes grow. Okay, so let's take one of these reaction diffusion equations and figure out how we're going to simulate it. Okay, so we have U and V are both going to be 2D arrays. And right, so those are the concentrations. So we have U, I, N, and this is going to be the spatial grid index. Oh, except that I'm in 2D, so I have to have IJ in fact, right? So instead of 1D, and this is the time step. So if I think about a spatial grid like this, I equals 0, 1, 2, 3, and then J equals 0, 1, 2, 3, etc. like that. And then there's some spacing here. So the spatial spacing delta x between grid points. And we have the same thing for V, right? Okay, so that's how we're going to discretize. So we're discretizing in space and discretizing in time. Okay, so the Bresselator model du dt has a du dt in it. So so let's approximate that with u ij of n plus 1 minus u j n ij over delta t. So n j or ij. Okay, so that's a first order approximation to the time derivative. So our equation looks like this: du dt is equal to du del squared u plus f u of u comma b. So all of the stuff on the right is not, there's no update in time. So I can put here u I j n plus 1 minus u I j of n over delta t on the left. And then this is all going to be stuff that depends on the current time. So I need an approximation for del. We're going to work on that next. Plus f of u. And actually the fu is easy. We can just take the current time. I mean the current position, the same position as this pen is dying. Why is it all my pens are dying? Okay. Oh, that's much better. Okay, so now I can multiply this whole right-hand side by delta t. So uij n plus 1 is equal to move this onto the other side. Plus delta t times this whole thing. Okay. So once I decide what's in here, it's pretty clear how I'm going to update the grid. So, and there's another equation that looks identical for v. So the scheme I'm using, first order Eulerian in time. I just upgrade so I can keep this whole thing, and everything in this is going to be a 2D matrix. And so everything on this side, right hand side, 2D matrix, and I have a new 2D matrix for u, and the same thing is true for v. So that's how things are going to work, or that's how the scheme will work. So the only thing I need to worry about now is how I'm going to approximate the del squared part of it. So that involves spatial derivatives. So we'll now use our, we need an approximation for the second derivatives on the spatial grid. So, so this thing is called the Laplacian. Sometimes people write it as upside down delta. So I need approximations for this. D squared u dy squared, like that. From the grid. So I looked at, we talked about approximating derivatives on discrete grids before, so I'm going to write down an approximation, and I'll show you that it's good to one order past. I think it's a first order approximation. So uj plus 1. Okay, so we have I and j. So let's take, how do I want to talk about this? So let's only look at the x part, and so it's u I j, where I is the x discrete and j is the y part. So let's just, I'm going to drop the j index for the moment. ui minus 1 minus 2 I over delta x squared. And that is an approximation for this. And I could put, now I can add the j part to make sure j, like that. And this is all at time step n. Okay. So this is an approximation for that. So now let's write down the approximation for this thing. It's uij plus 1 plus uij minus 1 minus 2 uij n, like that, over delta x squared. So all of this together is an approximation for that. So let's check. I'm just going to check one half of it. So u of I plus 1j. So this is u at x plus delta x, where x is the value at the I position. So this, I can do a Taylor expansion is equal to uij plus du dx at the ij position times delta x plus 1/2 delta x squared du dx squared at ij. So that's just the Taylor series plus order delta x cubed. And now we can do I minus 1, uij, and these could all be at the same time step. So I just dropped the n. And now because it's in the opposite direction, this is I minus 1. There's a minus here. X delta x plus, this is squared, so it doesn't matter what the sign is. Uij dx squared. So let's add these two and we'll subtract 2 of these. So u of I plus 1 plus u of I minus 1 minus 2 u of I. So there'll be 2 of these, and I'm subtracting 2 of them, and they'll all cancel out, so 0. Then this one, because I've added these, those 2 guys will go away. Plus 1/2 plus 1/2 is 1 delta x squared d squared u dx. So ui plus 1 plus ui minus 1 minus 2 ui over delta x squared is equal to order delta x cubed is equal to d squared u dx squared plus order delta x. Okay. So, so that's should make you feel better about the fact that this is actually, this approximation is consistent with that. And you can look at this and kind of think about, on the grid, what are we doing? If we have a position here, then this point here is the I plus 1. This point here is the I minus 1. This point up here is the j plus 1. Down here is j minus 1. And what we're doing is we're adding these two and subtracting that one. And so if it's curved, we'll see a signal. If it's just, if the slope of the gradient is flat, we won't see the signal. And you get information from these two, you get information about del squared in the x direction. And that using these 2 points, you minus the center again, you'll get information about the gradient in the y direction. So putting all these together, if I just add all these together, I have ui plus 1j plus u, that's to the right, ui minus 1 comma j, that's to the left, plus uj, ij plus 1, that's up, plus u ij minus 1, that's down. And then there's 2 of these and 2 of those, so that's 4 uij. And I divide by delta x squared. So yeah, so when you look at the scheme, the whole scheme is going to look like this. Uij n plus 1 is equal to u n ij plus delta t times this. Oh, and there's a diffusion coefficient, right? du plus delta t times f of u ij and fu uij. This is not u, this is v. Time at times step n. And that's the scheme that I wrote out for you in the example. With the same thing with another equation that's similar for B. And then these are the reaction things. Oh yeah, okay, so one more thing about the implementation. So these things and the boundary conditions. So we put everything on this spatial grid. What do you do at the edges of the grid? And the easiest thing to do with the edges of the grid is when I want a position near the edge, I just take the one on the opposite side. So that's called periodic boundary conditions. And so for the, and it's kind of a way to try and pretend that you're working on a really big space. You could get periodic behavior that's not real, but when you use periodic boundary conditions, but they're the easiest boundaries to use because you don't have to come up with any special rules on what to do at the boundary. So that's what's in there. So that means if I plus 1 is n, and so it goes past the grid, you just subtract n and put it mod n, and it will be back in within the grid. And there are these nice routines called roll in Python that will let you shift the whole array by 1 or by any number in any direction. And so, you'll get an array back that's shifted by whichever direction by however many indices you want. And so the easiest way to write these Laplacian operators up with single line, so instead of looping through every place in the array, you just use the roll command with 1, -1. And the roll command will take an axis. So you either use axis 0 or axis 1 for the 2D matrix. So I'm not sure which, the indices, it's never really clear. Fortunately, in this, which one is first, you check that if it matters. In this case, it doesn't really matter because you're taking left, right, and up, down exactly symmetrically. So if you rotated by 90 degrees, it wouldn't change the code, or flipped, it wouldn't change the code. So you roll by 1, roll by -1 on the first axis, and roll by 1 and -1 on the other axis, and then subtract off a not rolled version of the array times 4. Divide by delta x squared. And so that it's very quick to write this with single line commands. You don't have to do any looping at all. You do have to do looping to do the update. So I mentioned the boundary conditions. Yeah. So I think that's it. Oh yeah, I mentioned initial conditions. So I think that's it for this thing. It should be similar to what you guys did for the Kuramoto model, except kind of 2D now with patterns. Any questions about reaction diffusion equation?
So does your Laplacian approximation change if you're not doing periodic boundary conditions?
So does what change?
Because you said this was like your Laplacian approximation, right?
Right. So what do you do when you don't have a periodic boundary condition? Yeah, so you can come up with a different approximation for ddx squared that would be correct at the boundary. But then you have to decide, what do I want the boundary to do? Do I want the gradient to be 0? Do I want u to be 0? Like what type? I mean, didn't you take a whole class on boundary value problems? You have to decide.
Yeah.
Yeah.
No, I was just curious, like in terms of like the approximation specifically, like do you have to like make sure that it checks out? Because like when you wrote out those two summations, right?
Yeah.
Would those have to change based on the
yeah.
based
So
on
if, for example, you had you wanted your grid to have a special boundary, like fix u, set it to be 0 or something, then I can make a second order scheme for du dx squared that would only depend upon grid spacings to the left of the boundary or to the right of the boundary, depending on which side you are. So you can come up with things that don't require left, right. The stencil, sometimes people call these stencils. The stencil looked like this. It was this little X. And actually, as part of the problem, I ask you, for some reason, it's popular when people write simulations of reaction diffusion equations to use the diagonal terms. So they tend to add in, they make a different approximation to the Laplacian. So, so you can try that out. I actually asked you to try that out so you get a feeling for how to use this roll command. But Yeah, I tried it, I didn't see any difference, but yeah, so if you have a boundary, you can always develop whatever order scheme you want, just make it asymmetrical.
Yeah.
But for sure, dealing with boundaries, it has to be done specially, meaning, you know, you can't just write it down as a single line command. Now you have to go and say, I have to treat all the things right next to the boundary in a special way to give you whatever desired boundary condition you want. Like, so if you're doing a hydro simulation, you'd be like, is it an open boundary? Or if I'm simulating a trombone, what's the outer boundary look like? Well, it's zero pressure. What if I close, you know, if I'm doing a pan flute, then it's a closed boundary at one end and an open boundary at the other end. And then you've got excitations, right? So if you're modeling the mouthpiece, like what's going on there? So that's actually a bizarre boundary. It involves nonlinearities possibly. So you can see boundaries can be non-trivial to implement in code with a PDE.
Yeah, I just wanted to like, I knew it was going to be different, or I assumed it would be, but I just wanted to double check that, you know, this was explicitly for periodic.
Yeah, so this will work everywhere that's the nice thing about the periodic boundary conditions. The roll command will implement this everywhere mod n, for the n being the grid, and you know, yeah, so you don't have to worry about the boundary. It makes life simpler. Otherwise, we would be writing code and have a whole nother section on the boundary. And yeah, when I did have an example, I replaced the hydrodynamics example in this class with the reaction diffusion equations, and it's like getting rid of the boundary was such a relief. It's not that hard to write, but it's like one other level of things you have to worry about when you're trying to get your first PDE simulation up, you know? So periodic boundary is very convenient and easy to, there's no errors. Oh, the other nice thing about it, the roll, doing this with a roll is very efficiently implemented in Python. So you don't need to do any looping. You can use the roll and then make sure you calculate the boundaries afterwards. But it's very fast to write one-line commands that do array manipulations in Python. They're optimized somehow to be quicker than loops. So I've noticed that if you can write the code in terms of things like roll, it's a lot faster. So that's another reason. The boundary would probably, it's not a loop over the whole grid, but it would, you'd have to take care of all four sides, and that's actually pretty big size of things. Well, maybe not huge, but more complexity certainly. More questions? Boundaries, yeah. They can take a lot of time. They can also really affect the results of your code, which is either a good thing or a bad thing. If you're trying to change your code based on a boundary, or change the phenomena based on what you see at boundaries, it's a good thing. So it's like interesting. If you don't want the boundary to affect your results, and they do, then that's a problem. So behavior, so there's actually whole phenomena like turbulence that can be strongly affected by boundaries. Hydrodynamics often can be quite simple to solve away from boundaries, but the boundaries can influence the flow a lot. And so like, anything that involves vorticity, vorticity is generated in boundaries, vorticity is conserved away from boundaries. So, the whole calculation can be dependent upon what you do in the boundaries. That's a property of incompressible hydrodynamics. Okay, so more questions, or we're okay with that? We have a little bit of time. I think I just have enough time to talk about this symplectic integrator, since Haekong Allen mentioned that his integrator maybe gained energy. So let's go backwards and talk about. So I talked for a while about what it means to be incompressible in a 2D flow. And so incompressible with a 2D flow means volume is incompressible means volume is conserved, but in that the other a way you can talk about it is area. There's like a conserved energy, and trajectories don't approach each other. They just, so like the harmonic oscillator where you have circles that don't, there's no contraction or no expansion. The Jacobian is 1. That's another way of saying that. So volume is preserved in the flow. So, so there's lots of classes of models where there is an energy conserved, like Newtonian mechanics is that way. And if your system conserves an energy and your integrator doesn't, then over long term, you'll see these drifts that change the dynamical behavior. So one way out is to have an inaccurate but area preserving or energy preserving integrator. So I'm going to show you how to make one. So I'm going to write things as P and Q. I know many of you have not had classical mechanics yet, but just think as P is the velocity here. So this is a harmonic oscillator. So this is potential energy. And this is kinetic energy. And to make things simple, if I were doing a harmonic oscillator, mv squared plus 1/2 k x squared. So v is q, x is v is p, x is q, k is 1, and m is 1. So I just set all the physical parameters to 1 for this model. And this has a nice symmetric equation of motion that q dot is p, so that just means the velocity is p, and p dot is minus q. If you have a harmonic oscillator, x double dot is equal to kx with a minus sign. So with m equals 1 and k equals 1, then that's consistent with this because x double dot is p dot, right? So, but this is really nice and symmetrical, right? With the minus sign. And that minus sign makes it gives it what's called symplectic. It makes it what's called symplectic minus sign. So the mathematicians like to talk about symplectic manifolds, things that have the minus sign. Okay, so what's the solution of this? So so a general solution to harmonic oscillator is, something that oscillates, right? So we have Q of T is equal to, and yeah, so it's a cosine of T minus T0. That's a solution. And this particular, with all n equals 1 and k equals 1 is equivalent to saying omega is 1. And so P of T is just the time derivative of this, which is a sine, cosine goes to minus sine of T minus T0. And I can expand this out. Expand this out. This is a cosine of T times cosine of T0 plus a sine of T sine of T0. And this is a minus a cosine of T sine of T0. See if I get the signs right. Plus a cosine of T sine of T0. Q of 0 is equal to a cosine of T0. P0 is equal to minus a sine of T0. Oh wait, the signs can spell that. Right, so this this a cosine of T0 is Q0, and the a sine T0 is P0. So you can see I can write this out. This will be something times P0, Q0 something times P0. This will be something times Q0, P0 something times Q0. So the whole reason for writing this out is that I'd like a nice form for it. So Q of T and P of T, I'm going to write to look like this. Sine minus sine cosine of T Q0 and P0. So it's a matrix times the initial condition. That's just convenient. And now, so the reason I'm writing it like this is when we talk about an integrator, we start with variables at a particular time. And then we want to tell you, have a way of finding out what are the quantities at a little bit of time later. So remember, we took, when we solved, we came up with schemes for this, A of x, or f of x. So this was an ordinary differential equation, and we made integration schemes for it. We had a way of writing f to the n plus 1 is something that depends on x to the n, right? So we, do, and also depend on the time step. So that was the way we wrote a scheme. We would start with a particular condition, and we'd say, what's the value at some time later? So Runge-Tuttle was like that, for example. So this, I'm kind of assuming the time is small, and we're starting with condition Q0, P0, and I want Q and T at a slight time later. That's the idea. And that's going to give me a scheme that looks like this. So that's why I took some time to write it in this matrix form. So but one thing to notice, if I take the determinant of this matrix, cosine squared minus sine squared, it's actually, because there's a minus sign here, it'll be plus sine squared is 1. So the determinant is 1, and that's related to this thing, this behavior that there's a conserved energy and volume is conserved in the transformation from coordinates to the next time over. So to have this nice property where energy is conserved, the transformation from the current time step to the next time step should have determinant equals 1. And it does here. This is the actual solution. It has determinant 1. But supposing I do an first order approximation to this. So cosine to first order in t. So now let's assume t is like actually it's like dt. I want to find the new coordinates a little bit time later. So to first order, cosine of t is 1. So actually cosine of t is 1 minus t squared over 2 to first order, or to second order in t. So that's just the Taylor expansion of cosine t. And sine t is t plus or minus t cubed over something, 8 maybe, etc. So first order, sine t is t. So sine t is t, I don't know even. So qt and p of t. So here's an approximation. Q0, P0. So let's call this Q of n plus 1. Let's call this P of n plus 1. And then this will be Qn, and this will be Pn. Okay. So here's a first order approximation, first order scheme. But the big problem with the scheme is if I take the determinant of this scheme, 1 plus t squared, the determinant is 1 plus t squared. So what this scheme will actually do, the real harmonic oscillator with Q and P will have orbits that look like this. And this one will have orbits that do this. They'll spiral out. So, and that's because the determinant is bigger than 1. So, so let's show that in another way.
Sorry,
So,
I have a question quick.
yeah.
Does that change as you take higher order approximations for cosine and sine?
Yeah, so if you don't say I want it to have a determinant 1, so there's lots of ways of coming up with first order approximations. In fact, the way to fix this scheme is I can add t squared in here, and it will still be first order accurate. But I can I can just assert. In fact, that's the way I'm going to show you to fix this scheme. You just do 1 minus t squared here. And now the determinant is 1, and it's as accurate. They're both first order schemes, but this one has a determinant of 1, and so it won't do a spiral. So what I can do now is we can actually calculate the new energy after the time step. So with this scheme, so how do I calculate the new energy? Well, energy is, so this is equal to the energy. Only I wrote it out as a Hamiltonian. So I just take the new P and Q and put them in there, and we'll find out what the new energy is. So the new energy after taking a single time step looks like this. P squared plus Q squared times 1 plus T squared, where T is the time step. So, you know, after taking many time steps, it will increase. So, so what if I change it to this, T squared? And now I take the transformation, and so let's look at the transformation. So this was the old energy, but we're going to change it. So what's the transformation look like? So I have Q to the n plus 1 is equal to Q to the n plus T times P to the n, and P to the n plus 1 is equal to minus T times Q to the n plus 1 minus T squared times P to the n. And now I want to compute the new H. And so that's 1/2 P squared. And it's the Pn plus 1. So this is going to be the new H. And this is squared plus Qn plus 1 squared. When we plug these things in, what we get is this 1/2 P n plus 1 squared plus 1/2 P to the n plus Q, and Q here, squared, and then you get this cross term. And the cross term comes from these guys multiplied out. So yeah, so we get this. So what does this do? So with a harmonic oscillator, everything is kind of nice and symmetrical. Like this thing, it's like it pulls it diagonally a little bit. And so that we have an energy that's conserved, but it's a little bit tilted to the one side. So the trajectories look like this. So this is Q and this is P. So we have an error. And so you look at what is the error in energy. It depends on the time step. It depends on P and Q. But we're integrating a system that conserves energy. It just doesn't conserve the right energy. It's a little bit off. So the trajectory, instead of looking like this, looks like that. But what's the advantage? Well, it never spirals out. It always stays close to the original trajectory. So even though it's not very accurate, like the distance in energy space on this trajectory might be, in this case, it depends on T. So it could be pretty large, but it's never going to get very far away because it's always, you know, going to come back because it's stuck on trajectories that are similar to the original one. So that's the whole point. So this is like it will be well behaved forever. It will never, the difference between the actual trajectory and the real one, well, they'll never get very far apart because some energy is conserved, but you're not conserving the exact energy. You're conserving some energy that's close to the real one. So this is the whole idea behind what's called symplectic integrators. So that because they obey the symmetry of the problem, they never get very far away. So they're much better behaved on long time scales. And they integrate something that's close to the right system, not the right system. They also, I mean, there's also lots of dynamical phenomena that you don't lose. So like resonant behavior, the chaotic behavior, all of that is reproduced, just not exactly in the same positions, very slightly moved over because you're integrating an energy, but it's not exactly the same one. So one thing to notice about this, so these symplectic integrators, this little example shows you one of the properties about them. The difference between the real energy, that one, and the one we're integrating depends on the time step. So what happens if I change the time step? Well, if I change the time step, it's like I'm moving to a completely different conserved energy. And you get huge errors built up really quickly. So symplectic integrators, which are in general quite well behaved, don't work very well if you want you want the time step to vary. So they have this, you pay a price using them, and that's usually that you're fixed with a particular time step. So there are kind of ways around that. There's this procedure called regularization, which involves transferring to different variables so that you get a symplectic system that effectively lets you take smaller time steps when you need to take some, so the typical thing for the celestial mechanics setting is what if you're on an eccentric orbit and things move really fast when you get close to the central star. So you might want to integrate with smaller time steps when you're it's near the star. So if you multiply your whole system or change the units of time so that you wind up with a different symplectic system, then you can get an integrator that acts a little bit better in the A+, at the pericenter conditions. So those two are kind of clunky, so they have downsides too. So, but these are the types of things that people think about when they're looking at long-term solar system integrations. How do you improve them? So usually they have to be symplectic or extremely high order. So if you look at a code like Rebound, which right now is the most easy to get and used by Hannah Rain up in Toronto, he gives a bunch of integrators. They're either symplectic or extremely high order, like 8th order. So and you can integrate either way. If you want to do the job fast and see phenomena, you pick the slow order symplectic ones. If you have a situation where you might wind up with close encounters or something, you may need to go to the high order one, which is variable step size. So you may want that, but Okay, so there was one more thing. Yeah.
A quick question. Why? How do you know that you should subtract t-2 from the lower right term, not the upper left?
Oh, you could have done it for the upper left.
And the result will be similar.
Yes, you would also get symplectic integrator. So how do you generate symplectic integrators without some magic, meaning we just wrote down something we knew worked? So one thing you can do is you can take your Hamiltonian, divide it in pieces, and then make your symplectic integrator from pieces of symplectic integrators, all of which you know how to solve. And so you alternate taking steps from the different pieces. So what are pieces? So for Keplerian ones, we know Keplerian orbits really well. So often symplectic integrators are designed from pieces of Keplerian orbits and interactions between planets. So interactions between planets, those are like potential terms. So they change velocities, but they don't change positions. And the symplectic orbits. So it's like you integrate bits of orbits and then you let little kicks come in from the planet interactions. Each piece of those is symplectic. So the total integrator would be symplectic. And you can generate that's whatever order accurate you want by doing little summations of these things. So the way to figure out how to construct a high order one is to look at the operator. You think about it as an operator is an exponent, and whether the exponentials, you expand the exponentials essentially for operators. So that one is Yoshita's approach. It's really nice. It's nice in the sense that you can generate 4th order ones without too much difficulty. Often people are using 2nd order ones actually in the symplectic setting. And then it's not magical. How do you make it symplectic? It's like pieces of symplectic transformations give you a symplectic transformation. And symplectic transformations are just evolution of things you know about, like Keplerian orbits or interactions with potentials, things like that. So yeah, so that's a general way to construct them. Yeah, so there's one
Does-
more thing. Yeah, question?
Does the so I'm not gonna lie, I don't know a whole lot about like the concept behind like what I'm about to ask about, but does this have something to do with like is this similar to like a simplex minimization? Because that's something I was doing with like in a physics 403 thing, and I don't know a whole lot about it, but he was talking like Bensby was talking about like a projection of something and how it like kind of moved around. Do you know about simplex minimization at all?
Simplex, so simplex usually means a loop of some sort. So kind of different, not the same as symplectic,
Okay.
which has got to do with this -1 in the it has a -1 in the transformation. So I think those are different.
Okay.
Whenever you use simplex, the word simplex, it usually means like you're thinking about little loops or little integrations over small patches.
Yeah.
But,
It's
yeah.
and I just wanted to see if they were related at all. And like I said, I don't know a whole lot about it, but I was just curious if you knew if they were related.
Sounds like you're doing a minimization, and minimization is not a volume preserving type of thing often. So I'd be surprised if they were that related, but I don't know that setting.
Yeah, no, I was
Yeah.
more curious about like the numerical side if they were similar, but yeah, no, I got you. I was just curious.
Yeah, well, I haven't talked about minimization. So there's a lot of numerical things that require you to minimize to find things, so like if you're doing fitting, for example, often you're minimizing chi-squared or
That's
something.
exactly what
Oh
fitting.
yeah, okay, so minimization routines, there's like huge volumes of techniques and how to do that. Oh yeah, we could have spent about a whole month on this if we wanted to. I chose not to, but yeah, it's not hugely boring, and it's very useful. Minimization for fitting, or not just fitting, finding best, optimized things. Often you construct something and you want something that's the best possible thing, minimizer for this quantity, right? Yeah. And then there are various ways to achieve that. And so anytime you create a function that it's complicated that you want to minimize, it could have local minima, for example. How do you get the fastest way down to the bottom without getting lost in some, complicated landscape? So there's various approaches to doing that. Yeah, it sounds like that's what you're talking about.
Yeah, that's it. And we talked about a lot of those things too. So, but yeah, no, I was just curious was all. Thank you.
Yeah. Yeah, so the last thing I wanted to mention is a stencil. So I guess we have like 1 minute.
It's 15.
Yeah, 1 minute. So when we look at integrating on this versus that, this thing I can go in this direction and I can go in that direction. I get the same orbit. So if I flip the velocity and flip the time, I get the same thing. So these are both called reversible. And so simplex, the setting where volume is preserved means dynamics is reversible. When we look at the Runge-Kutta, which is the second order Runge-Kutta, we're generating, so it was a midpoint method, right? And we generate values here, and then we use the values here to predict the, so if this is T0, this is T0 plus H over 2, this is T0 plus H. We use this midpoint calculated here to predict the next point, but this is not symmetrical, we can't go backwards. And so one other type of integrator, you start with a position here, and you use this to predict, to get the, to use this point, you start with a position here, use this point to get a position here, then you use this point to get a position there. But these types of mechanisms, so this one's called the leapfrog because you've got two things leaping over each other. So stencils that look like this are time reversible, and they don't have to be symplectic, but the fact that they obey time reversal symmetry makes them act as if they were symplectic. And so integrators that are based on time reversible, enforce a time reversible symmetry are often better behaved on long time scales for things that conserve in energy. than things like the Runge-Kutta, which are not time reversible. So, so you can think about integrators that way too. So, I mean, the basic idea, just like everything in physics, if there's some asymmetry in the actual problem that you want, if you exploit it to make your numerical method obey it, chances are you're going to get better behaved numerical simulations or approximations. So kind of a theme with physics, right? Yeah. Okay, so we'll end there. You guys have the reaction diffusion equations to work on over the weekend. Oh, I checked the schedule and there are 2 weeks free at the end of term. So plenty of time for your project. Actually, it's not as tight as I thought it would be because somehow I missed a week in there, but I fixed the calendar, so it's good. And next week we'll start talking about random walks. So we're going to shift gears for a couple weeks, talk about random processes. So I'll see you on Monday on campus.
Thank you.
Bye.
See you Monday.